and welcome to week 7. We're now into unit 10, quantum and nuclear chemistry, so something a little different. We're going to get started with the lesson on 10.3.1, which is fission, fusion, and radioactive decay. So click in to get started. It's about 30 pages long, so we'll do the first 15 for this screencast, and then we'll do the next 15 for the second part of the week. Okay, so as we start with this, it's kind of just talking about, radiation. We've heard of these words before, especially when people are talking about radiation treatment for cancer and different things, that radiation can cause cancer, but it also can cure it. And so why is it both dangerous and helpful? We have radiation in the environment, like ultraviolet radiation. So is that something we're concerned about? It does burn our skin and different things going on. So we're going to learn in this kind of unit that how nuclear power is produced, where, the energy in nuclear weapons. We've heard of, the bombs and different things that are going on. And then also how the sun also produces so much energy as well. So you can get kind of that answer going on. So there are 3 main types of nuclear changes. So we're going to first talk about nuclear fission, and we're splitting a nucleus into 2 or more parts. Okay, and this is what happens in a nuclear power plant. Then we have nuclear fusion, where we fuse something together. We join 2 or more nuclei together, and it's happening in the sun's core right now, all the time. And then we have the last one we're going to talk about is radioactive decay. Is this spontaneous breakdown, so something that happens just on its own, of unstable nuclei, which releases particles or electromagnetic waves. And so that's kind of the last thing we'll talk about this. So they've kind of split up with 3 different nuclear changes that happen in chemistry. Okay, so uranium is often one, the uranium bomb and different things going on that we have that is an important part of nuclear chemistry and nuclear fission. So what's happening below, if we look at this image below, we have a neutron hitting the uranium, and it's causing it to split. When the nucleus splits, remember that nucleus is that middle part of the atom, the number of protons changes, so it's no longer uranium. Remember, whenever there's a proton change, that it changes the element. And so the uranium transforms into krypton, barium, and then it has 3 extra neutrons. Okay, so there's kind of something that's happened when we talk about this, like fission, which it's splitting this atom. Have you ever heard of like fissure in the earth and everything? It's like a split. That's kind of how I remember fission is the splitting. Okay, so the change in mass, once it's like splitting apart of the nucleus, determines how much energy is produced. Okay, so and then a lot of energy is produced and is released during this kind of reaction. And so the nuclear power plants that we have all over the world, this is kind of the reaction they're going with. They're having these uranium rods, and they're collecting kind of this energy of this splitting of these atoms, these nuclei. Okay, and so Einstein, and most of you have seen the E equals mc squared, and this is kind of where it comes into play. E for energy, and M for mass that we're talking about right here. We're not really mentioning C, but we're talking about E and the M, okay? And the more mass of the nucleus that is changing is the more energy, the E, that's going to be produced in the nuclear reaction, okay? So that's fission. Let's look at fusion for a second. So fusion is, fusing together. You're joining the nuclei together. So these 2 different nuclei are coming together, and then they're also splitting off this neutron that's kind of splitting off as well. If you look at the blue kind of figures, they're coming together, but then the 1 neutron kind of spreads off by itself. Okay, so we do have some of that happening below. So 2 isotopes of hydrogen are fusing together to form 1 helium, and then an enormous amount of energy is also released with this as well, and because they're fusing together, and this is what's happening in the sun's core. You've got hydrogen, gas, and flowing, in the sun, and so they're bumping into each other, fusing together, making helium, which is releasing a lot of energy. So that's the sun. And so the mass of the nucleus of an atom changes a great deal because you're like doubling it, well, at least for the 2 hydrogen atoms. And so much energy is released per the atom. So we have these 2 differences: fission, the splitting apart, or fusion, they're coming together. So they kind of want you to kind of assign what's going on. So we have small elements joining together to make larger ones. They're fusing together. The sun, again, like I said, it's fusion. When we talk about splitting, we got fission. So splitting. Okay, and then the last bit, the nuclear reactors are fission as well. Okay, so a simple little review of what's going on there. Okay. So what they also noticed is that a helium atom has a nucleus of 2 protons and 2 neutrons. We know that by looking at the periodic table. It's mass number 2, atomic number 2, and the mass number is 4, so 2 protons, 2 neutrons, okay? If you compare the mass of the helium, though, of these, so if you, this is like, for example, this is helium, they're all combined together, the 2 protons, 2 neutrons. But if you weigh them separately, it's going to be a different weight. So it's kind of weird. They have the same 2 green, 2 pink, but they found that there's a missing mass when it's together, and they call it a mass defect, okay? So in the nucleus, the whole is less than the sum of its parts. So the whole helium is less than each of the parts if you added them together. Crazy. This mass defect has to do with the force that holds it together. So that force that's holding us together is kind of replacing the mass that's missing. And we mentioned this a little bit earlier and before, but the force that's holding the nucleus together is called a strong nuclear force. Okay, call it just kind of a force. It's like the glue that holds it together. Okay. With this as well, the missing mass is then turned into energy to hold that nucleus together. So the strong nuclear force stores that energy and holds the nucleus together. This is called the binding energy of the atom, and so we have the E giving the binding energy and the formula of the nucleus, and M is the missing mass or mass defect. So that's more what it's about, what's going on. Okay, so a small amount of mass, I mean, we're talking about atoms and stuff, and especially hydrogen, the smallest atom in the sun, but a small amount of mass can provide a great deal of energy. Okay, they're talking about the binding energy within a single one atom of helium is 4.53 times 10 to the negative 12 joules. That means that 1 gram of helium, which, if you convert the grams and the molar mass and whatever, is an energy of 6.8 times 10 to the 11 joules. Now, how long would you guess that it's going to, power a television just with 1 little gram of helium, 1 gram? It actually, weirdly, is going to power it for 108 years straight. Okay, there's a lot of energy in these nuclei and different things going on. Kind of crazy. Okay, the last little bit. So we talk about splitting nuclear fission and joining together nuclear fusion, but they both are producing energy no matter if you split apart or put together. They're both producing energy, but kind of the rule is that fusion produces when there's small atoms involved. So you're fusing like hydrogen, like helium. You're fusing small atoms. When you have fission, it's producing energy when large atoms are involved. Okay, like uranium and the kind of elements in the lower, like really bottom of the periodic table and different things going on. Those are going to be the bigger atoms are going to break apart in fission, and they'll produce more energy then. Okay, so it kind of goes through that a little bit. Okay, so let's look more though so fission, fusion, and leave that be, and then look at the third part. And we're going to start with radioactive decay, a little bit of it, and then we'll leave the rest for next time. So you have alpha, beta, and gamma decay. And you might have heard of some of these, maybe. And they, A, B, and then gamma, the Greek symbols. So they're particle waves through space. And so we have alpha and beta decay are going to release alpha and beta particles. We'll talk about what they are. And then gamma decay is actually going to just release electromagnetic waves of gamma rays. So they're not going to have like an actual particle that is released. Energy is released in radioactive decay, but it's much smaller than fission and fusion, so it's not going to be as much. And it's produced much less than the fusion and fission. Okay, so we're looking at ionizing radiation versus non-ionizing. Now, they're not going to memorize which one is each. And so they just kind of mention this. So kind of just read through and be familiar with it. You're not going to need to know as much the difference, but there's something that is bad or damaging to human tissue versus like somewhat okay, low energy rays as well. Okay. So let's talk about alpha decay first. So we're going to have alpha decay is where they can change the number of protons. Well, they can all change the number of protons, okay? So it's going to become a completely different element when that happens, okay? And so we call this a transmutation. It's changing, okay? Mutating, changing. So in alpha decay, an alpha particle's release. Now, we remember an alpha particle being 2 protons and 2 neutrons. So the release of one alpha particle causes a change, okay? So, for example, we have uranium down here, 234. Okay, that's the isotope. That's the mass number, not the atomic, okay? And remember that uranium, 92 protons. If we looked at the periodic table, we could find that for uranium, U. And then neutrons would be, 234 minus the 92 equals how many neutrons are in that nucleus. Okay, so let's show what happens. So what happens is that an alpha decay causes it to lose 2 protons, okay, and 2 neutrons come off in the form of an alpha particle. So it's a completely new element, okay, once it has changed the number of protons, okay. So now we got to figure out, well, what is it? It's now thorium-230. How we could figure that out, we could go to the periodic table and find number 90 because it was 92. It lost 2 protons and went to 90, and I could go to the periodic table and find that, and now it's thorium. Okay, so how do I write that, or how do I look at that, or what do we call that? So we call uranium the parent element. The new element that's formed is called the daughter element, and then there's an alpha particle that's it's just the 2 protons, 2 neutrons. Okay, so we kind of write it into an equation. It's a decomposition because the decomposing is pulling apart. So you have uranium-234 is the parent, thorium-230 is the daughter, and the alpha particle is the particle that is released, or the splitting particle. So another way we can write that is in numerical form, and this is some of the things that we used to write or kind of have or kind of view. That top number on the top left is the mass number. Remember, it's protons plus the neutrons. Okay, so uranium is number 92. That's what we find on the periodic table. 92 is the atomic number, the number of protons. Okay, so helium, so for example, what is the correct way to write this? It has 2 protons and 2 neutrons. Now it's not going to be 2 and 2, because remember, the number on top is our total. Add those 2 together. So the number on top should be 4. That's our mass number when we're adding those 2 together. And the bottom is the number of protons, which is 2. So it's B. Okay, last little bit. Let's finish 2 more. Okay, so in this, we can have a whole equation. It looks complicated in the middle, but it's really not bad. It's really subtraction. So we start with uranium-235. They'll tell us this. It has number 92 off the periodic table. Okay, so they'll tell us the number. We're going to put that on top, and then that's the number from the periodic table. Okay, and that you will often have, and we'll use that a little bit later. Okay, so helium is that alpha particle. It's 4 and over 2, the mass number of 4 and the atomic number of 2. That's always what the alpha particle is going to look like, how we write it. So all you do is subtract. 235 minus 4 equals 231. That's what I wrote over there. 92 minus the 2 equals 90. Okay, what this is kind of saying, if I added these numbers up, like 4 plus 231, I'd have 235. 2 plus 90, I'd have 92 on the left side. It's like splitting those 2 apart. Okay, and that's all it is. So for example, what are we going to do? So we have curium-247 has gone through alpha decay. What are the parent and daughter elements? Well, if it's going through alpha decay, it's automatically the parent. So we can eliminate 2 answers. It's not B, it's not D, because curium is the one we're looking at, so it's the parent element. Now, we need to know if americium or plutonium is the daughter element. Well, I look through the periodic table. Now I need to find curium first and find out what number, and then subtract 2 because it's lost 2 protons. Okay. So curium is down here. Curium is number 96, and if it loses 2 protons through alpha decay, I go 1, 2, it goes to plutonium, and that is the daughter element. So it is A. Okay. And then last, because I'm running out of time, you're going to do the same thing. You're going to subtract over. What is this? 234 minus what, you have to subtract over. You're going to get B. Okay. So I will continue with part 2 soon, but kind of work through this and good luck.